Hey everybody, with this video we're going to walk through a multiple linear regression modeling example where we are being tasked with finding out if there's some combination of remote sensing satellite imagery metrics and other spatial ancillary data layers that we can use to predict the yearly growth of red spruce. So in other words, just what we know about the site and from a satellite picture, can we look across the entire landscape and see how well red spruce is growing in terms of their basal area increment? That's what BAI stands for. So let's head into JUMP and get started with that. Now, because we have so many possible input independent variables, right? So many possible pieces of information that can be used to model this. We're not going to have enough observations in our 34 plots that we've collected actual growth data on to be able to use these all. We would run out of degrees of freedom. So we have to use a stepwise regression, which is a way of looking at the data and figuring out the best combination of variables to include. And we get at that through our fit model platform. So I can enter my response variable. I have this continuous basal area increment response, and I have all of these possible input predictor variables. So I'm just going to add them all. Again, this is so complex we would be way overfitting this model because we know that with only 34 observations we probably don't want any more than 3 predictor terms using that 1:10 ratio of predictor variables versus observations. So I need to change this to a stepwise regression. And now when I select run, and I can keep this open in case I want to come back to it, but now when I select run, it opens a new window that gives me some different options on how I want that stepwise regression to be selected, how I want it to be run. And I think that for us right now, the easiest and most straightforward is just to use this p-value threshold. So if we use a p-value threshold and we change this direction to mixed, what it's saying is that it is going to look at the individual one-to-one relationship between each of these and basal area increment, the response, and it's going to put in the most significant one first. So it's going to look at all these p-values and it's going to find the most significant variable, looks like it's right there, and deposition, and it's going to put that into the model, and then it's going to go back and it's going to look for the next most significant variable, and then it's going to enter that into the model, and then it'll reevaluate the model. If when it adds a new variable, one of the other ones that was already in there is no longer significant, it will actually go back in and take that out. So that's what mixed direction means. It means it will add things that are significant, but if at any point one of those variables that is already in the model becomes insignificant, it will pull it back out again. And if you didn't like that, you could go just forward. So forward just keeps adding them and adding them until your threshold is reached. In other words, until there isn't anything as significant as your threshold to add in. Backwards starts with them all in and takes them out one at a time, which is sort of what we did before with the factorial ANOVA. But mixed is really going to get us closest to what we want. And I vote that we use our typical 0.05 thresholds as the probability threshold to either put something into the model. It has to be at least significant at the 0.05 level, or if it is no longer significant at the 0.05 level, pull it back out again, right? So now I can just press go and it selects the best model that meets these criteria that we've set, and we can see that it's only bringing in 2 variables. Well, that's good because we didn't want to have any more than 3. Just to give you an idea of how this might change, we could just remove them, and notice before this was set to 0.25, and that's because JUMP assumes that you're sort of doing a data mining exercise. So you'd like to know anything that's even sort of relatively close. So just as an example, if we had those less conservative limits, we could see that there would be a lot more variables that would make that cutoff. All right, so that's just giving you an idea, but let's go back to our original conservative thresholds. I was happy with that, just that 2-term model. So you can see how things were entered, and then removed, and yeah, it walks you through all the steps if you'd like to really get into the details of it. But now that I think I'm going to be happy with this, I can just run this model. Okay, so now I've just brought back in the group work guide so that we can make sure that you remember to think about all the different things you should be thinking about with a multiple linear regression. And then we've got our output from running this model over here. So the first question is, what's the maximum number of predictor terms you should allow? Well, we already talked about how really you don't want any more than one predictor variable for every 10 observations that you have in your data set. And we had 34 observations. So we know we don't want to have more than 3 predictors. So that's great, and we meet that criteria, so we know we're probably not just overfitting the model. The next question is asking for the actual equation, the full model equation, so that we know what this regression model is. The model is actually the math, and that's down here in this parameter estimates table. We know we have an intercept value, so this is our intercept, our beta naught right here. And we know we have 2 significant terms, both significant at the 0.01 level, and that would be the NDWI, Normalized Difference Water Index, from the previous year, and its beta 1 coefficient would be a negative 4739. Don't worry, you don't have to give me a million decimals. That's kind of crazy when the numbers are already this big. And then our second variable was nitrogen deposition, and its beta coefficient was negative 97. Right, so if we were going to try to actually look somewhere across the landscape and predict red spruce growth in areas where we had not gone and measured the basal area increment through tree cores, we would take this number, we would then subtract this number times whatever the NDWI value was for the previous year, and then we would also subtract this number times whatever the nitrogen deposition was for that year. The next question asks us if we have any high leverage, outlier high leverage points. And we know that one commonly used diagnostic for that is to go in and ask from the saved columns in the magic red triangle for the Cook's D influence values. So remember, this is one of the few things from the magic red triangle that is not going to just show up tacked onto the output. Instead, what it's done is it has added another column to our original data table, right? See, here it is, Cook's D influence has been tacked on to the end. And I want to actually go and just analyze the distribution of that to figure out if I have any extreme outlier data values that are high leverage points. In other words, that are overly influencing the regression coefficients such that if they were removed, the regression model would change. And it does not appear that I have any outliers. I don't see any points showing up beyond these whiskers in the box and whiskers plot. So it doesn't seem that we have any high leverage points that we really need to worry about. The next question asks if we have any autocorrelation issues within our predictor variables. In other words, is this minimum NDWI correlated with N deposition? And if so, that would probably make our model unstable. So we can get at that by right-clicking within the parameter estimates table and ask for the variance inflation factor. Anything higher than 10 means that we have probably a high autocorrelation that we should be worried about. Both of ours are really low, down around 1, so no, we do not have any autocorrelation between these two variables based on our variance inflation factor. Okay, then the next question says, well, how accurate is your model? Well, we can report the R squared. This gets at how much of the total variability in red spruce growth we can account for just with these two terms. But accuracy is a little bit different than just saying how much of the variability. It's literally how accurately can we predict the basal area increment. And we can get that by taking the root mean square error, right? That's how far off we are on average, and dividing that by the mean of the response, right? So on average, what percent are we off with our predictions? So we could just pull up a calculator to figure that out. So 473 divided by 1244 is 38.38. So we are about 38% off every time we predict on average. On average, we can predict with accuracy that's around 62% and error that's around 38%. The next question is how robust our model is. And when we say robust, what we mean is that if we brought in totally new observations, new data, that this model would still fit. So in other words, it's not just really fitting to these specific 34 observations. And if we brought in new locations, it would still work. And one of the ways we can get at that is with an independent validation, but we don't have a whole bunch of independent data. So instead, we're going to ask for the jackknife residuals, which we can get from the press statistic here in the row diagnostics. So now we've got a press root mean square error. So this means that when we jackknifed all of our residuals, in other words, make a model by leaving one observation out at a time, predicting back on that observation and seeing how far off you are. On average, with those jackknife residuals, we are off by 490. And the general rule of thumb is that as long as your press root mean square error is pretty close to your original full calibration root mean square error, you probably have a stable model. And the ratio is typically 1 to 1.5, and we are much closer than that, between 473 and 490. So it does seem that we have a robust model. And the next question is asking, how meaningful is this model? Where this is where you put on your ecological thinking cap and you think, well, okay, I know we have a significant model. I know all my terms are significant, but is 61% of the variability, is that actually useful to somebody who wants to be able to look at red spruce growth across the landscape without having to go and core all of those trees? And I would think about all of the other possible environmental variables that are also influencing red spruce growth. And to me, when I think of all of those, soil chemistry, water availability, root compaction, pests or pathogens, extreme weather events, competition from surrounding trees, solar radiation, to me, to be able to account for 61% of the variability with just basically a drought index and nitrogen deposition, which tells you how stressed red spruce is by acid deposition, I think that's pretty important. I think that's meaningful and useful to me. So even though I knew that I'm off by, say, 38%, I can still get a relative assessment that I think will be useful across a larger landscape. So you may have interpreted this differently, but as long as you're justifying your interpretation, then I will accept it. And then it's just asking you to summarize. So considering all of these things, right? Considering how many terms you have and how significant they are, and the outliers and autocorrelation and how robust it is, considering an independent data set and how meaningful it is overall, do you think that this model is useful? Can somebody use this to assess red spruce growth across the landscape? And again, you may interpret this differently, how you want, but I tend to think, and again, I'm biased because I am a remote sensing person, but I tend to think that it's worth sacrificing some of your accuracy to gain perspective across the entire landscape, right? It's sort of like two different ways of studying something. You can go down on the ground to a small number of plots and you can truly understand exactly what's going on there, but know nothing about what's happening across the full forest, across all red spruce. Or you can look at a landscape scale assessment where you don't know exactly what's going on, but you know relatively what's going on. And you can then use that to make assessments about the larger population. I actually think they're both important, so I think that both approaches should be taken and then used together to understand what's really happening with red spruce growth across the landscape. And it actually turns out, because this is real data, red spruce is actually increasing in its growth over the past 7 years. So it's actually experiencing a resurgence since acid deposition stressors have been reduced on this resource. So really very exciting. Wow, that was it. So 14 minutes to run through a regression model and explain it all. Hopefully this makes sense to you. I also have the answers written in as feedback on the responses that you submitted via Blackboard. So between that and this little video, hopefully you are now all set to take on more multiple linear regressions. Good luck.